Alright, looking at this problem, we have a couple of variables that we need to consider. So first, what change in volume occurs if 60 milliliters of gas is cooled from 33 degrees Celsius to 5 degrees Celsius? So the two variables that we're looking at are volume and temperature. The law that pertains to volume and temperature is Charles' law. Just a quick review of Charles' law. We know that Charles' law says that if temperature goes up, an increase in T equals an increase in volume. Volume is dependent on temperature, and this makes sense because as gas particles gain kinetic energy, they're going to start moving faster and with more force, thus being able to increase the amount of empty space that they have between them. So we would see an increase in volume as a result of increasing temperature. Now we need to figure out which formula we're going to use to help us solve this problem. The formula that's associated with Charles' law is V1 over T1 is equal to V2 over T2. V1 is the initial volume. We want that unit in liters. T1 is the initial temperature. Remember, we must convert degrees Celsius into Kelvin. And how we do that is we add 273 so that we can convert from Celsius to Kelvin. V2 is the final volume. That is what we're calculating because we want to know what change in volume occurred when 60 milliliters was cooled from 33 degrees Celsius to 5 degrees Celsius. And then T2 is the final temperature, 5 degrees Celsius, and we'll convert that into Kelvin as well when we get ready to solve our problem. So, before doing this problem, let's think about what our outcome should be. We want to know the change in volume. And the temperature is decreasing. It's going from 33 degrees Celsius to 5 degrees Celsius. So we should see a decrease in volume when we go to answer this question. If it's anything above 60 milliliters, we will know right then that we are incorrect. So let's get started on this. We have V1, our initial volume is 60 milliliters. Remember, we have to convert out of milliliters and get into liters. Move the decimal 3 times to the left to do that, so you would have 0.060 liters over 33 degrees Celsius, converted into degrees Kelvin. Remember, it's just 33 plus 273, or 306 Kelvin. And that's equal to V2, which we're going to leave because that is what we're solving for, over T2. 5 plus 273 is 278 degrees Kelvin. So here's our work. We need to organize this a little better. So let's take it out. Let's set it up as a proportion where we're just going to cross multiply the numerator of one side by the denominator of the other. And so if we rearrange this equation, it's going to become 0.06 liters times 278 Kelvin is equal to 306 Kelvin times the final volume. Now we need to solve this algebraically. We can combine the terms on the left side. When you multiply 0.06 by 278, you get 16.68 liter kelvins. Remember, we cannot cancel these units because they're not like terms and we're not dividing, we're multiplying. We're going to set that equal to the other side of 306 Kelvin times V2. Now we're going to divide both sides by 306 Kelvin so that we can cancel our like terms on this side and have V2 by itself. And then we're going to divide 16.68 by 306 Kelvin. And now cancel out the Kelvin units because those are like terms. We're left with liters, which is the unit we want because we're solving for final volume. And so it is 16.68 divided by 306, which gives you 0.0545 liters is equal to V2. And there's your final answer. For comparison purposes to the initial volume that was given to us up here in the question in milliliters, we can convert this out of liters and go into milliliters. If you wanted to do that, just move the decimal back to the right 3 times and you would get 54.5 liters. Not liters, sorry, milliliters is equal to V2. So let's compare this volume to our original volume that we were given in the formula, 54.5. We were given 60 milliliters. We did have a decrease in volume, so this does match Charles' law. Since we had a loss in temperature, we had a loss in volume.